So Ricky will tell us today about Bernstein's theorem and applications to enumerative combinatorics.
All right, thanks everyone for coming. Yeah, so as Avi mentioned, so I'm going to be talking about polynomial systems. So in particular, counting solutions to polynomial systems and in relation to this geometric quantity called mixed volume. So this is going to be largely an expository talk. So my plan is in the first half of the talk roughly to basically sketch the statement of this theorem, Bernstein's theorem, about counting solutions to polynomial systems, and as well as sketch a proof. And then in the second part, to give a couple applications just to various interesting enumerative problems. So let me describe the basic setup. So we have some system of polynomial equations. So maybe I'll write the system. F1 in variables x1 through xn is equal to 0. So we have 2. Of course, we should, if we want a finite number of solutions, we should probably have the same number of polynomials as variables. Here, each of my polynomials, I'm going to assume it's some polynomial with complex coefficients. To some extent, these results still hold if you replace this complex field with other fields. I'll say a little bit more about that later, but for now, let's just stick with the complex numbers. And so we can ask, suppose you have such a polynomial system, how many solutions would you expect? How many solutions? So just to make this totally concrete, let me just do kind of more specific situation. So maybe I have 2 polynomials and 2 variables. So maybe I have 2 polynomials, f of x, y, g of x, y. And let's just say that they're quadratics. So what is that, x squared plus xy plus cy squared plus f, and similarly for g. So if I have 2 quadratics, how many solutions should I expect? Well, of course, if you just plot the solution sets for each of these 2 quadratics, each one will define a conic. And we would, generally, if you pick 2 conics, you usually expect that they intersect in 4 points. So usually 2 conics. Of course, this is not always the case. So there is a few weird things that can happen. So one thing that can happen is, for instance, maybe your conics just intersect in fewer points. So they can intersect in fewer. And there's a few ways this can happen. So maybe your conics happen to be tangent at a given point, and then that point counts as like a double point. A kind of bigger problem is that sometimes they would kind of intersect at points at infinity. Like maybe you have like 2 parabolas like this, and they should sort of both intersect at this point, sort of infinitely high in the y direction. And so either something like this, or if you have like 2 tangencies like this, can cause you to intersect in kind of fewer points than you expect. It can also happen that 2 conics could intersect in infinitely many points. So I mean, one silly way that this can happen is if your quadratics are just like the same, but there's multiples of each other, and then they intersect at every point. A less silly way is that maybe your quadratics both factor as a product of 2 lines. and then they share a line in common.
Actually, I have a silly question. So in the first picture, how do they meet at infinity?
So these are both parabolas, and so I mean, if you sort of drew this picture instead of the sort of affine plane, you drew it in the projective plane, then both of them would contain the point at infinity in the upward direction.
So I mean, the results you will state will be in the affine case or the projective?
It'll be in the affine case.
Okay.
I mean, well, one can be a little bit more precise about where it holds, but that involves like torque geometry to sort of figure out how to correctly close up the affine space to deal with these sort of boundary situations. But I'm not going to talk about that today. Okay, so what was I saying? So, or they can intersect in infinitely many points. This is like, for instance, if they share a line. But certainly, you know, one can avoid these situations if we say that. So these points, you know, if they intersect in infinitely many, these points of intersection differ from these situations in that these points are not isolated points of intersection. That is, you know, an isolated point of intersection is one where you know, there's some neighborhood around this point where there's no other points of intersection. And that does not happen if they share a line, for instance. So one can say that there are always, at most, 4 isolated points. So here are the isolated points again. They don't count, for instance, a line of points. And in fact, one can say a little bit more, which is that you know, if you were just to choose the coefficients of your polynomials essentially like randomly, these situations are not going to happen. So the reason is because, like, if you just choose 2 conics randomly, like the condition that they're going to be, for instance, tangent, is some kind of algebraic condition on the coefficients. So, you know, you'll plug the coefficients into some algebraic equation, and that if that equals 0, then your 2 conics are tangent. And if you just kind of choose the coefficients randomly, that's never going to happen, or it's going to happen with, you know, essentially 0 probability. And so what this means is that if you choose your quadratics, you know, kind of randomly, or the technical term is generically, then actually these situations will not happen, and they'll actually intersect in exactly 4 points. So equality holds for so-called generic choices. Coefficients where, again, you can take generic to mean just you know, a randomly chosen collection of coefficients, or more technically, that the coefficients don't satisfy some algebraic condition. Okay. And so, of course, where does this number 4 come from? So this was, you know, recognized way back in the day, perhaps as far back as Newton, probably. So why 4? So the answer is that there's a theorem, which is called Bézou's theorem, which says that suppose you have a polynomial system such as this one, then in general, how many solutions do you expect? Well, you should just take the product of the degrees. So in this case, you have 2 quadratics. You expect 4 solutions. So this polynomial system that I've written up there has at most the product of the degree of fi isolated solutions with equality more generic choices. Coefficients. That is, if you fix the degree of each fi, and then for a given degree, you pick your polynomial coefficients essentially randomly, then you'll actually get exactly the number of solutions, which is just the product of the degrees.
Ricky, it's good if you cannot, if you don't get font size too small, too much smaller. Okay.
Okay, I'll try to write a little bit larger.
Yeah. So, but another point is this product of the degrees. Maybe another really simple example: if the polynomials are on distinct variables, like if you had x1 to the d1 is 0 and x2 to the d2, sorry, x1 to the d1 minus 1 is 0, then x2 to the d2. So then you see plainly that you have the product of the degrees.
That's right, yeah. So, sort of building, you can sort of see it should build up from kind of the one variable example, as Bobby mentioned. Okay. So as we'll see, this Bézou's theorem will be a consequence of the more general theorem, which I'll talk about, which is, sometimes you have polynomial systems, and this bound is maybe, will give you something which is much larger than you actually think should happen. And the reason is because a lot of times you're not going to be considering like a general polynomial of degree 2, for instance. Maybe you'll know something about this polynomial. For instance, maybe you'll know that it's actually a sparse polynomial, that its support is rather small. And so we can ask the question, what if the fi are known to be sparse? And so we're going to consider the situation where maybe we have our polynomial fi. Here I'm using x just to denote the set of n variables, x1 through xn. And maybe we know that here A is some tuple. Maybe we know that its support is some finite set. So here AI, you can think of some subset of z to the n. I guess if we want positive exponents or non-negative exponents, I should take like, natural numbers to the n. But I'm actually going to also allow Laurent polynomials, which is not going to make a big difference because we're actually going to count solutions where all of the coordinates are non-zero anyway. So even if I have negative exponents, I can kind of just multiply through to get rid of those without changing the number of non-zero solutions. So suppose for each fi, I select some subset of essentially exponent vectors ai, and then I stipulate that fi has to have that support. So again, these coefficients cia, they're going to be complex numbers. So for each fi, I choose its support, and then I ask how many solutions should I expect for such a system. So let's do an example. So I'm going to do an example which is kind of similar to this quadratic example, except I'm going to pick supports for my two polynomials. So maybe I'll take my first polynomial.
Ricky?
Yeah.
Just for the example I mentioned just a minute ago, maybe it will be easier for me to understand your notation. If the the two polynomials was x to the k equals 1, and the second was y to the l equals 1, then right. Then in this case we will have just the sparsity would be 2, right, for each of them.
Right. So your first set would just be if the first one was x to the k plus 1, then you take the exponent vector, which would be of the monomials. So it would be k0 and 0, 0. So that would be your a1. And then for the other polynomial, it would be like 0, l, 0, 0, 0.
And 0, 0. Okay. So it will be each of the sizes will be 2, even though the number of solutions will be like k times L.
Right. Yeah, so we're going to care not just about the size, the number of non-zero monomials, but we're actually going to care about which monomials they are.
Good.
Because as we'll see, what's going to end up being important is the Newton polytope of the polynomials. And so in your example, the Newton polytopes are still of large size. They have sort of length k and L, and so you still get kind of a lot of solutions. Whereas it can happen that the Newton polytope is if it's of different shape or something, then that can have more of an impact on the number of solutions than the actual number of distinct monomials.
Okay.
Okay. So let's do an example. So maybe f is some quadratic, and I'm going to assume that its support is relatively small. So maybe it's going to be of the form ax squared plus let's do dx plus ey plus f. So here the support, so a here, it's a1. So this is the set 2, 0, 1, 0, 0, 1, and 0, 0. So if I were to draw it, it would look something like this triangle. The points in this triangle, these 4 points in this triangular shape. And then maybe I'll take gxy to be, for instance, let's do p prime xy plus p prime x plus p prime y plus y prime. So here a2. So if you just look at the exponent vector, so it's just 1, 1, 1, 0, 0, 1, and 0, 0. So you get this sort of points in this square. Here you get the points in this. Okay, and what do these look like? So, I mean, if you were just to graph what these guys look like, so f, of course, is just, this is, if you set this equal to 0, there's just the equation of a parabola, what that opens in the kind of vertical direction. Right? So this, roughly speaking, is something that looks like this. This guy, if you graph it, what you'll get is a rectangular hyperbola with the asymptotes parallel to the axes. So maybe something that looks like this. And if you just try to visualize how such things can intersect, it should not be too hard to convince yourself that actually, if you have such a parabola and such a hyperbola, then they will intersect in at most 3 points. Okay. So these. So somehow what's going on is that, again, if you sort of were to do the projective picture, both of these kind of contain a point at infinity in the vertical direction, and that sort of gets lost from the Bézier bound of just 2 times 2, which is 4. That point up there kind of gets lost because we don't actually see it in the affine picture, and so we only get that these can intersect in 3 points. And so the question is, how can we get this number 3? And the answer is given to us by the main result, which I want to talk about, which is called Bernstein's theorem. So this is sometimes also given more names, as theorems often are. So this is also known as the Bernstein Bernstein, Kushnarenko theorem, or sometimes just PKK theorem. This is from roughly the mid-70s. So what does it say? So it says that the sparse system again, here I'm assuming that the support of Fi is AI, so support. This has at most some number of isolated solutions. So I'm going to just write this expression and then explain what it is in a second. So it goes this many isolated solutions. In C minus 0 n. So again, this is only counting non-zero solutions with equality for generic choices of coefficients. And so let me explain what this number is. So these P's, these are the Newton polytopes of the polynomial. So just the convex hulls of these sets AI. So here, P is just the convex hull of AI, or the Newton polytope. Of F. I. And then this MV is this function that takes n polytopes and spits out a number, and this function is called mixed volume. So because the definition of mixed volume is a little bit complicated, I will have to talk for the next part of the talk about the definition of mixed volume, but suffice it to say that the kind of quick and dirty definition is that how can you get this mixed volume? So if you look at the volume of the following polytope, so this polytope, this plus denotes Minkowski's sum. So what do? So you take these n polytopes and you scale them up by certain factors, lambda 1 through lambda n, and then you take the Minkowski sum. So just you take points here plus points in here plus points in here. This together is some probably larger convex body, and you can compute what its volume is. And it turns out that this is a homogeneous polynomial, actually, of degree n in these parameters, and this mixed volume is defined to be a specific coefficient in this polynomial.
So Ricky,
yeah,
I don't know how comfortable the people are who have never seen adding bodies in Rn. So so that's the two comments. I mean, first of all, the mixed volume of just one body P1, just one convex body P1 will be just its volume times lambda 1, right?
That's right. So if I just had one, sorry. So do you mean if you're taking the mixed volume of 1. So the number of polytopes is generally equal to the dimension that your polytope.
Yeah, so in one variable, that's fine, yeah.
lives in. So if you have a one-dimensional polytope, then certainly it's the mixed volume of that single polytope is just going to end up being its volume, because then you'll just have you'll have one term here, and then it'll be the volume, which is length of lambda times p, and that's just lambda times the length of p.
Right. So yeah, sorry, I meant the polynomial itself will be the length times this lambda 1.
Right.
And maybe you could also, since you said what mixed volume is, like adding the points, maybe you can just show the sum of two lines or two line segments in the x and y direction.
Right. So I mean, let me do a more specific example of this. I can do, for instance, this example here. Okay, so let's look at this example that I wrote here. So here, so P1 is going to be, again, the convex hull of these 4 points here. So that's just going to be this triangle like so. So P1 is just this triangle. P2 is just going to be that square. Okay, and then I want to take this kind of linear combination here, where I take lambda 1 P1 plus lambda 2 P2. So how do I do this? So first I kind of scale up P1 by lambda 1, and I scale up P2 by lambda 2. So maybe let me scale up, since it's a square, that's easier. Maybe I'll scale up P2 first. So first let me scale up P2. So I'll get just a bigger square of side length lambda 2. Here, let me do it this way. So if I scale up lambda P1 by lambda 1, so I'll get sort of this right triangle that looks like this, and then I'll be adding it to this sort of bigger square. So great, I want to take basically points in here and then add them to points in here, and then look at the convex shape that I get out of it. So one way to think about this is kind of like, this is the origin here. So if I sort of pick up this triangle and kind of smear it so that this point sort of hits all of the points of this square here, then it's like I'm adding every point in here to every point in here. So you can imagine I sort of just pick up this triangle and just sort of smear it across so that this bottom vertex covers all the points in here. And what will I get? So let me draw this guy again. So up here, I'll get something that looks like this. So I'll get sort of every point in here, right? I just took this triangle. If I just sort of smush it around here, then it'll just cover every point inside this sort of funny shaped pentagon. And of course, it's this is just it's a two-dimensional pentagon, so it's very easy to compute its volume just by summing up the volumes of these pieces. So if we compute what the volume of this thing is, so we will get, so this guy is like lambda 2 squared, and then we have these two rectangles. This is lambda 1 times lambda 2, and then this is 2 times lambda 1, lambda 2. And then we have this little triangle here, which has volume lambda 1 squared. And so the mixed volume is the coefficient of this mixed term here. So the mixed volume is this number 3. And so this agrees with this sort of exercise that we did here, where we visualized that these two quadratics intersect in at most 3 points. Okay. So I'm going to talk a little bit more about mixed volume and do some special cases. But any questions so far? So then why is this true? Okay. So, I mean, mixed volume is actually kind of an interesting thing. It's like, it's a little bit hard to sort of get a good picture of what it looks like geometrically. And often, kind of the most useful way to sort of work with it is just by using various properties that it has. So let's discuss a few of these. So an easy example is, what if all my polytopes are just the same? Maybe all my polytopes are just a single polytope P. Then what is the mixed volume? Well, I can just essentially compute what this thing here is, right? So we get the volume of lambda 1p plus dot 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 plus lambda n p. Of course, this is just, you're just scaling up p by the sum of the lambdas. This is the volume of lambda 1. This volume is n-dimensional volume. So when I scale by lambda 1 through lambda n, it just raises it to the multiplier to the nth power. So this will just be equal to just lambda 1 plus the dot plus lambda n to the n times the volume of p. And then I want to take the coefficient of this mixed term. And so that's just, by the multinomial theorem, going to be n factorial. So the middle term coefficient. Is just n factorial, and then times, of course, this factor here. So this is the mixed volume. Okay. And so what does this mean? So this corresponds to a special case of Bernstein's theorem. So suppose you know that all of your polynomials have the same support. So you fix some support for all your polynomials, and then you choose, say, generic choices for the coefficients with fixed support. Then the number of solutions is probably going to be just essentially the sort of scale with the volume of the support, the volume of the new polytope. So often this is one of the most common cases in which you would actually apply this, because maybe you are choosing your polynomials in some way so that you know what their support is. So let's do another case.
Or if your all your polynomials were linear functions, then they will all have the same support, right?
That's right.
Yeah, and then you would get the mixed volume will be what, the permanent of the.
I mean, if all of your polynomials are linear, then the Newton polytope would just be like the elementary simplex. So the the exponent vectors that appear are just 1 0 0 0 0 0 1 0 0 0, and as well as if you have constants, the origin. So in that case, P is just kind of the elementary simplex in Rn, and its volume is 1 over n factorial. And so this would tell you that the number of solutions you would expect is just 1.
1, okay.
Of course, if you have a system of linear equations, and you have the appropriate number, you would expect to have 1 solution. So let's do a different case. Let me mention one property of mixed volume. So mixed volume. This turns out to be multilinear in each coordinate. What do I mean by multilinear? I mean, in the usual sense, with respect to Minkowski sum and the usual scaling. So if I scale a particular polytope by a factor, then that will scale the mixed volume by that factor as well. Or if I replace a given factor with the Minkowski sum of two polytopes, right? If I have something like, if I have A P1 plus B P1 prime, and then a bunch of stuff, then this will equal, assuming A and B are non-negative. So this is actually like not super obvious, but one can derive it from.
I have a question about the Newton polytopes.
Yeah.
You always assume that they contain the origin?
So no, they do not necessarily have to contain the origin.
If my support is 1 point, just like I have one coefficient.
Yeah, so if your support is 1 point, then it will turn out that the mixed volume is always going to be 0 in that case. And that's again, we're only counting non-zero solutions. So if your support is 1 point, then that means you have just a monomial equaling 0, and that will not have any non-zero solutions. We'll see where this sort of non-zero condition comes in. It's a little bit funny, and actually counting solutions where you're allowed to have zeros is somewhat more subtle. But this at least guarantees
when you say non-zero,
Yes.
when you say non-zero, do you mean every coordinate non-zero, or do you just mean non-zero?
You cannot have any coordinate equaling 0.
Okay.
So you didn't write it quite like that. I mean, it's written, minus 0 to the end. Good.
Yeah, you take out 0 and then you raise to the end. It's not Cn minus.
Excellent. Yeah.
Thanks.
Okay, so we're not going to use this multilinear property too much, but let me just point out how you can, for instance, deduce Bézout's theorem from this. So, suppose you have some polynomial which is sort of generic of degree d. Then what is the support of f? Well, you just have to have all exponent vectors, non-negative exponent vectors, such that the sum is at most d. So if you look at the Newton polytope, so here then the support of f, maybe I'll write convex hull, the support of f is just going to be basically d times kind of the elementary simplex here, where delta is just the convex hull of 0, and then your standard basis vectors d1 through dn. So you'll just get this, in 2 dimensions, you'll just get this, right triangle here of side length d, where all the points whose coordinates sum to at most d live. And in this case, suppose you know that each of your polynomials f1 through fn is just some generic polynomial of some degree, d1 through dn. Then, in order to compute the number of solutions, we should be taking the mixed volume of all of the polytopes that we get in this way, various multiples of this elementary simplex here. So so if Fi is generic of degree di, then the number of solutions to the system should be just the mixed volume of these polytopes here. So d1 delta, d2 delta, so forth, dn delta. And because this is multilinear, we can just pull out all these factors. And each of these deltas is this elementary simplex, which has volume 1 over n factorial. And so if we just plug that in here, we'll see that the mixed volume of the simplex with itself n times is just going to be 1. So this will just be just the product of the degrees, which is exactly what we would expect from Bézout's theorem. So you can think of Bernstein's theorem as giving you a generalization of Bézout's theorem, and it actually matches, gives you exactly the same bound in the case where you have generic polynomials of fixed degrees. And one more example that I want to do is just the example where each of the polytopes is just just like a segment, a one-dimensional segment. So suppose Pi is just a segment, so it's just the convex hull of 2 points. And I'll just make the points be, I'll take the origin and then some other point. Maybe I'll call it A. Maybe I'll write it. I'll call it AI. Like this. So here AI is some point. Let's say AI1 through AIN. Okay, well then in this case, again, how do I compute the mixed volume? I have to scale each of the PIs, compute the volume of their Minkowski sum. Of course, this is just going to be a parallelopiped, right? Because I just have n segments. And when I sum them together, I get some parallelopiped. And the edges are just going to be lambda 1 times A1, and etc. lambda n times an. And so the volume is just going to be, I have these scaling factors, and then I have basically the determinant, which is determined by these vectors ai. That's the determinant of a1 here, and then a2 here. I guess absolute value, just to be safe. Okay, so in other words, this is just going to be the mixed volume of A1 through Pn with the absolute value, of course.
So the mixed volume ends up being the volume, the actual volume of the parallelepiped.
That's right. It just ends up being just the volume of this parallelepiped. Okay, so what does this mean for Bernstein's theorem? Well, let's see what it means. So this Pi is supposed to be just the convex hull of these 2 points. So that means that each of my polynomials Fi should just be a binomial with 2 terms. One of them is just going to be essentially a constant, and the other is just going to be a monomial, which is given by this vector ai. So in other words, my equations are going to look like, so this corresponds to a system that looks something like, my first equation is going to look, maybe I'll write it down. So my first equation is going to look something like x1 to the a11, x2 to the a12. So this is, this is the term that corresponds to this point here, and then equals some constant, let's call it c1, that corresponds to this point here at 0. I guess I should have two generic coefficients here, but I just divided out by one of them. So I only have one, this constant here. And then that's my first equation, and the second equation will look something like this. Equals C2, and so forth, right? And so the claim is that this system, the number of solutions, for generic choices of these constants, should actually just equal the determinant of this matrix. So let's see why that's the case. So the claim is that actually solving a system like this is very similar to solving a linear system of equations. So let me just let A be the matrix where I just basically just this matrix here. Okay, so if you have some integer system like this, one way that you can try to solve it is to do row operations and turn this into an upper triangular matrix. So this is usually called putting A into Hermite normal form. So let me write what that is. So we can turn A using row operations into some, again, integer matrix, which is now upper triangular. And we can do this using basically unimodular operations. So we can write this as some row operations is multiplication on the left by some matrix U, such that the determinant of U is plus or minus 1. So this is Hermite normal form. Right, so these U's are going to be switching two rows or adding some multiple of some row to a different row. And it turns out that if you do some row operation on A, you can do a very analogous operation on this system of equations. So if you scale, a given row by a constant, then that corresponds to just raising the same equation over here to that power. So that will just multiply all the exponents by that constant. And then if you add a row here to another row here, that just corresponds to basically taking one equation and then multiplying it to another equation. And so you can just do the same operations that you did on this A to get to H to turn this system that you started with here into a triangular system. So
Ricky?
Yeah.
Ricky? Yeah. Is it the same as simply taking your original polynomial system and taking logarithms of both sides and getting linear equations in the whose matrix is the A and whose variables are just log of xi?
Yeah. So it's the same thing. As
so then one can see that you are solving that particular linear system.
Right. I was just wary about doing logs because of complex numbers, but yeah, it's essentially that. So this will turn into a system which looks something like x1 to the h11, x2 to the h12, dot xn to the h1n is some now new constant. And now when you have this triangular system, it's very easy to count the number of solutions. Because first, you can just solve for xn. of course, it's raised to this power h and n, and so you have to choose one of the roots of this Cn prime here. So there's h and n choices for this last guy, and then you just plug that into the previous guy, and there'll be, again, you'll get, something to some power equals some constant, and so you'll have to choose which root you get in that case, and so forth. Eventually, you'll get all the way up to the top. You'll have to determine x2 through xn, and then you'll need to choose which root to take for this guy x1. And so the number of solutions here will just be just the product of these exponents. But of course, this is just the determinant of this matrix H. I guess absolute value, just to be safe. And that's the same as the determinant of the original matrix A, which is what we wanted to show, right? Because each solution here just gives us a solution to this original system, and we wanted to show that the number of solutions is equal to the mixed volume of these polytopes, which is again equal just to the determinant of this matrix. Okay. All right. Any questions about the example so far?
Is there any similar type of theorems for real solutions?
I guess I'm not sure,
I think it gets more complicated.
What was the question?
The question was whether, if you want to count real solutions, there are similar theorems.
Yeah.
Sort of. But then the sparsity matters, right? Then you might try and take into account the actual support, like what monomials you get. Like this a binomial over the even x to the n variable to a power equals a constant over the complex numbers has the power number of solutions, but over the reals has like 1 or 2 solutions. So then the sparsity versus just the degree, I think, starts to matter. I think it gets a lot more complicated. Sort of.
Yeah, there are some results on like few nomials where you have systems in each, maybe each polynomial has only 3 terms in it. What can you say about the number of solutions? But generally such results are harder to come by. Okay. So let me say one word about a kind of geometric way of seeing what this mixed volume is in terms of something called a mixed subdivision. And this will also kind of give an argument as to why this volume, this linear combination of the polytopes, why is it actually like a polynomial in these parameters. So one way of seeing this is by constructing something called a mixed subdivision. So let me go back to this example that I had before. Remember, previously I did this example with this right triangle and this square. And then when I computed some linear combination of these things, I drew some picture which looked sort of roughly like this. Maybe I'll color code it, because I have lots of colors here. Maybe I'll make this triangle red, and this triangle blue. Sorry, this square blue. So suppose this is my P1 and this is my P2. Then if I have P1, let me just take the ordinary Minkowski sum of P1, P2. So again, what it looks like is, I have this square here, and then I have this triangle, maybe I'll put it here, and then I add these guys together, and I get these 2 extra rectangles here, which I will draw appropriately with colors like so.
taken that for the purposes of.
Blue. Okay, so why have I drawn it like this? Well, if you think of what this picture will look like when you scale up P1 and P2, right? So when you scale up P1, right, it's going to essentially multiply all of the red edges by a given factor like lambda 1. And what's going to happen is like this square is going to stay the same size, but then this triangle, of course, is going to stretch by a factor of lambda 1. And these two rectangles will like stretch in one direction, right? This guy will stretch vertically, and this guy will stretch horizontally by lambda 1. And similarly, if you multiply P2 by lambda 2 and then add, then that will stretch all the blue edges by lambda 2 and keep the red edges fixed. And so what you can see is that like some of these cells, like each of these cells will scale by a different amount. So like this red guy will scale by lambda 1 squared, and this blue guy will scale by lambda 2 squared, and then these special rectangles will scale by lambda 1 times lambda 2. And so if I'm interested in the mixed volume, like I'm really interested in this kind of mixed cell here, because that will give the volumes of these guys will give me what the coefficient of lambda 1 times lambda 2 is. And so if I have a special subdivision like this that sort of scales nicely when I scale the polytopes that I'm summing together, then I can just read off the mixed volume using just the volume of certain cells here. And so this kind of subdivision has a special name, which is, it's called a mixed subdivision. So more specifically, what is a mixed subdivision? So mixed subdivision of, so let me call Q just the Minkowski sum of each of my polytopes Pi, is a subdivision. So a subdivision, if you have not seen before, you can just think of it's a way of cutting up this big polytope into a bunch of smaller polytopes. And there's a condition about how the pieces fit together. So like, they have to fit nicely along faces and things like that. But, it will not be super important for us to go into too much detail here. But the important thing is that each cell, C, should be a Minkowski sum on its own, where each of these Ci is equal to let me say it's the convex hull of some set Si. Si is just going to be a subset of the points that I'm interested in, Ai. So here I'm given that Pi is equal to the convex hull of some points.
Is there some distinction between just that and saying Ci is a face of Pi?
It's slightly more general because Ai could have points in the middle of the polytope. So this could be finer than just taking faces. So I want each piece to be basically a Minkowski sum of something from P1 and something from P2. So like this triangle is just this whole triangle plus this vertex, and this rectangle here is like this edge plus this edge, and so forth. And then there's an extra condition, which is that the sum of the dimensions of these pieces should just equal n. So this is so that they actually kind of, basically the summands from each piece will sort of behave independently from one another. Like, if I took an edge from each of them, then the sum would just be like a parallelepiped, which is sort of very easy to work with. Whereas, here, if I'm taking the sum of two-dimensional things, like I just get this weird mess. So this sort of guarantees that when I take the Minkowski sum, basically like there's each point in the Minkowski sum can be uniquely written as something from C1, something from C2, and so forth. And then there's a technical condition, so plus technical condition. Which is just about how intersections of these cells work. But again, it will not be so important for us. But the point is that if you have this mixed subdivision, then the mixed volume will just be the sum of the volumes of the so-called mixed cells. That is, the ones which are just sums of line segments. So the mixed volume is total volume of the so-called mixed cells. These are the cells where each of the pieces that you're summing is just a line segment. So these mixed cells will all look like parallelepipeds because you're just summing a segment from each of the individual pieces. So they're like the rectangles in this picture. When you scale up each of these polytopes by certain factors, then those are the ones which will be scaled exactly by just the product of the amounts that you're scaling by. Whereas the other pieces will get scaled up by this will get scaled up by lambda 1 squared. The other ones will get scaled up by things with other values. And so just to give you a sort of more interesting example of a mixed subdivision, I'll just draw one over here.
It will always be the sum of n factorial bodies. Or not?
No, you can have, it does not necessarily have to be, the number of mixed cells can vary, but the total volume is always fixed. I'm trying to think. Yeah, so for instance, let me draw another mixed subdivision of this, which only has one mixed cell. So for instance, if I, instead of putting the blue square P2 here, I put the triangle, then I could have something that looks like and then I could actually just split the, I can split this square in half and get something that looks like this. And so here now, this is my mixed cell. Or these were my mixed cells before. So the number of mixed cells can change, but you'll know, you can figure out what the volume of this thing is, and it'll just be the same as the sum of the volumes of these.
I guess in the binomial case, there's just one big mixed cell.
Yeah, you can think of the binomial case as just a giant mixed cell, but if your pieces have higher dimension, then you'll usually get these non-mixed cells, which contribute to the other terms in this volume computation.
Right.
Okay. Okay, so how does one actually find a mixed subdivision? So it turns out that there's kind of a standard way of constructing a mixed subdivision. And sort of similar to, there's a standard way to just compute, say, a triangulation of a polytope. And so let me describe how that works. So how to find mixed subdivision.
Font is getting
Smaller.
tending towards small.
Okay. I will try to write it bigger. So the basic idea is that you can do this kind of lifting thing. So let me draw a picture here. Suppose first I want to just find a triangulation of a polytope. Maybe it's like a square or something like this. One way I can do this is I can lift each of the points, each of the vertices, or in general, each of the points in AI. I can lift them up to a different height. So maybe I'll lift this guy up to some height like this, and this guy up to some height like this. Maybe this guy I'll lift to a lower height like this. And then take the convex hull of the points upstairs. So these guys, the convex hull of these points will probably be of one higher dimension, as I've sort of lifted things up to one higher dimension. And now if you look at this polytope up here, some of the faces are kind of on the top of this guy, and some are on the bottom. So the ones on the bottom are the ones where if I take a normal vector to the face, the vertical component is positive, whereas the ones on the top, the vertical component is negative. So if I take the ones which are on the bottom, so maybe that's like, in this case, this face here, and then this back face here, and I project them down onto the bottom, then it'll sort of give me some kind of decomposition of this polytope downstairs. And so basically what I've done is I've just assigned to each point some number, there's the height, and then I've gotten out of this some subdivision of this polytope downstairs. So first, for each PI, choose height functions. Let's call them W, say from AI to just real numbers. And then we're going to lift every point to one higher dimension, A, and then this height. And then take convex hull, take the lower faces of the convex hull. And then if you project down, these will give, switch boards here. If you project down, this will give a subdivision of each PI. These. And then once you've done this, now you kind of just take the Minkowski sum of all of these pictures. So take I have this sort of situation where I have PI down here as some polytope, and I have this thing up here, maybe I'll call it PI hat. And if I take the lower faces of this projects down something here, and I have a bunch of these similar. Then I take the Minkowski sum of all of these pictures, so I just take the Minkowski sum of all the polytopes down here. So here I'll get some big polytope. This now is Q, which is the Minkowski sum of these things. And then upstairs, I'll get some lifting, which is just the Minkowski sum of these polytopes up here. Which will project onto, even though I've gone too big here, which will project onto this. And again, if I take the lower faces of this Q hat, then that will project onto some subdivision down here. And the claim is that that will actually just be a mixed subdivision. And the reason is because if you look at the lower faces of this guy, so this guy up here is a Minkowski sum of these things here. And so each face of a Minkowski sum is going to be a sum of faces of each of the pieces. Because if you think about it, right, like a face of a Minkowski sum, you can think of this as just like it's the points here which are maximizing some linear functional. And so you can just look at the faces on each of these guys that maximize that functional and take their Minkowski sum, and that will give you just this corresponding face here. So all of the lower faces here are just Minkowski sums of appropriate faces on these guys. And then one can check that it satisfies, it will usually satisfy the conditions of being a mixed subdivision. One has to be a little bit careful because, mixed subdivision not only has this condition of each cell being a Minkowski sum, but it also has this thing about the sum of the dimensions and this other technical condition. But it turns out that if you choose the heights basically at random, for generic choices of heights, then this subdivision that you get will be a nice mixed subdivision. So for generic choices of heights, okay. So this is a way that, again, you just sort of pick heights for each of your points and then do some sort of taking of lower faces to get a subdivision of Q. And so the reason why I am even talking about this at all is because, as we will see, this is going to be sort of key to the proof of Bernstein's theorem. And I've been talking for a long time, so let me check.
Yeah, but
Yeah, maybe it'd be a good time for a break, and then when we come back, I'll try to finish the proof of Bernstein's theorem.
sure. And well, certainly we want to make sure you finish the proof.
Right. Yeah, I think there should definitely be enough time to finish the proof.
Okay, excellent.
As soon as, well, I'm scrolling down. I don't think there's that much. There's that much more. So, okay. So let me turn this off. Okay, so this is going to be a proof of Bernstein's theorem. I'm going to call it a sketch because I'm going to leave out some of the more technical details, but most of the key ideas will be here. This proof is adapted from the one by Huber and Sternfels. This is roughly 95. Actually, it's not too dissimilar from Bernstein's original proof, but sort of the reduction to these mixed cells is sort of the contribution of Huber and Sternfels, whereas Bernstein used kind of a different inductive approach. But it was sort of similar in style. Okay, so how do we do this? So remember that we have this polynomial system, which looks something like this. So we had all these FIs, we fixed their support, namely these AIs, and then we chose generic coefficients perhaps here. So what we're going to do is we're going to construct a new system with an extra parameter. So we're going to construct a new system where we have these new polynomials fi hat. So these are going to depend on x1 through xn, as well as an extra complex parameter t. And how are we going to do this? So basically, for every monomial, we're going to just attach a power of t. Okay. So this is going to be it's going to be the same sum, except we're going to multiply this by a certain power of t. And the power of t is going to be, well, we're going to choose it separately for each monomial. So this is going to be some function, maybe I'll call it wi of a.
So this is just the height function you chose before.
Right, so this wi I can take just to be, you can think of it as just a height function that I'm lifting every point, this wi. I'm lifting every point to some height. Of course, since it's an exponent, I want to choose it to actually be an integer as opposed to just a real number, but that's not going to be a big deal. So here, wi is some function from ai to just.
So if the point little a, if the vector a, the exponent vector a belongs to a1 and a2, they will get the same height?
No, they'll get, the height depends on which ai, the little a.
It's not really a function of a. It's a function of.
It's a function from a. Oh yeah, okay.
Yeah.
No, because wi depends on I.
Yeah.
And it's from ai
yeah. Okay. It depends. For every I, you know, in the same monomial, you know, x squared y cubed, in one polynomial can get one height and another height in another polynomial.
Right. I mean, in practice, that probably doesn't even matter that much because we're just going to be choosing these w's to be generic anyway. So probably one can get around such restriction, but for now, let's just keep them separate. Okay, so what's the deal with this new system that we get? So the key thing to note, of course, is if you let t equals 1, so then fi, maybe I'll say like as t approaches 1, fi hat is just going to approach fi. But if I want to solve this new system, then what does it mean to solve it? Well, I want to express x1 through xn as some kind of algebraic function in t, such that, you know, when I plug x1 now as a function of t through xn as a function of t into this thing, then all of these polynomials are equal to 0. So for as t varies, the solutions to this new system vary algebraically.
It's not clear that it's algebraic, right? I mean, if it's a quintic polynomial in T, then you will not have a...
That counts as algebraic. Yeah, I don't mean, you know, it doesn't have to be by radicals or something, but just the fact that these are polynomials means is what I mean by algebraic here.
Okay, yeah.
So, you know, what does this look like? So, you know, maybe I'd have a certain solution, these points, you know, when t equals 1, and then as I let t vary, these solutions will sort of trace out these various curves. And each of these curves is some algebraic curve. So it's given by some algebraic equation. And each of the isolated solutions for t equals 1 will kind of lie on a different branch of this curve. So what we're going to end up doing is we're going to solve or try to solve this system not at t equals 1, but close to t equals 0. So we're going to count the number of solutions to the system close to t equals 0. And then the claim is that the number of solutions will be the same if you're close to 0 or you're at 1. And so the reason for this is just kind of a general fact from algebraic geometry, which is that, like, if you have some sort of map between, you know, in this case, you're taking the curve, which is just the set of all solutions of this system, and then you have some algebraic map, which in this case is just the projection onto the last coordinate, then kind of the number of pre-images at any point will generically just always be the same. Okay. So in other words, it's only going to matter if we can find, for a generic point, the number of solutions, and then we'll be able to conclude that that number actually bounds the number of solutions, even at t equals 1. So what we're going to do is we'll try to solve the new system for t in the neighborhood of 0. And then I'll just say algebraic geometry tells us that the number of solutions will be the same as for t equals 1. I should say, even though I'm saying like that algebraic geometry tells us this thing, in practice, you can actually use the solutions that we find around t equals 0 to compute the solutions at t equals 1. So basically what we're going to do is, near 0, we're going to compute some sort of power series that tells us what the curve looks like near that point. And then you can use some sort of Newton's method and just sort of trace this curve all the way back to t equals 1 to actually find the solutions at t equals 1. So even though I'm sort of invoking this sort of fact here, you can actually get the solutions in sort of a very concrete way. You could probably also replace this fact by just some sort of implicit function theorem to get this sort of same result. But certainly I just know it from algebraic geometry about sort of algebraic degree. It's basically we're trying to compute the degree of a certain algebraic map. Okay, so let's figure out what happens near t equals 0. So and these are x of t. Okay, so how can we write these things down? So it turns out that there's a special kind of power series which one can use to basically write down any branch of any algebraic curve where the coefficients here are, there are some polynomials in T. And so these are called Puiseux series, which probably are not so common unless you've sort of studied similar things before. So these solutions lie in the field so-called Puiseux series, Puiseux series. I'm actually sorry how do you pronounce this. Okay, so what is this? So you can think of this as just, it's essentially just it's a Laurent series, except you're allowed fractional exponents. So, a Puiseux series will generally look something like this. And K0 is allowed to be negative here, so you can think of this is just a Laurent series in t to the 1 over n for some big number n.
So
but
n will be fixed for all the exponents, this common denominator.
Right, yeah, so you can't have, there has to exist such an n for all of your exponents. So you can't have to the half, to the third, to the fourth, and so forth.
And this is true for all the equations simultaneously.
Yeah, so if you have one for several equations, you can just choose a common, you can just choose the least common multiple
Good.
of n
Okay.
for different series.
Got it. Yeah.
So this field of Puiseux series, again, you can just think of it as the union of, this is essentially the union of the fields of Laurent series in T to the 1 over n for all n. And union here really means direct limit. You know what that means. But the point is that this field of Puiseux series is actually the algebraic closure of the field of just Laurent series, formal Laurent series in T. So this field sometimes might be denoted C race T. So this. This is sometimes called the Puiseux theorem or Newton-Puiseux theorem. Yeah, actually, Puiseux series go back like all the way to Newton, although probably he did not do some of the more formal aspects of it. Okay, so again, our goal is to solve this system, and so if you have a Puiseux series, then any given series has kind of valuation, which is just this essentially this lowest exponent that appears. And of course, as with power series, if I'm kind of plugging in power series into a polynomial like this, and I compute this thing, in order for this to be 0, I need, for instance, that the lowest degree term that I get in this will also have to be 0. And so what's going to happen is that when I try to compute basically what the lowest degree term can be, then sort of figuring out what all the valuations, all the lowest degree terms of all of these variables x's, the possibilities for what that can be will essentially correspond to the mixed cells in the subdivision that we saw earlier, and then the number of solutions will end up being the volume of that mixed cell.
So Ricky, I'm not sure if that's the right intuition, but here is exactly where the reduction from a general polynomial to a binomial happens. For each polynomial, there will be only one exponent that matters. Yes?
Yes, essentially, yes.
That's the exponent with who is hardest to get to 0. All the higher ones will get to 0 faster.
Right, yes. So somehow, once you can do the low degree terms, which will only, again, depend on essentially one, a binomial from each polynomial. Once you sort of get the lowest degree terms settled, then it's kind of very easy to sort of figure out what the higher degree terms will be. And so reducing to these lowest degree terms is what reduces to essentially the mixed cells in the subdivision that we saw earlier. But let me quickly sketch sort of how it is that we get from the lower degree terms to the other terms first, because that will turn out sort of not to be the difficult part, and it will just basically be essentially a form of Newton's method. So I'm just going to do a one polynomial case, and it will work analogously for higher degree polynomials. So again, you should think of this as just a system of one polynomial, and the system is just going to be x cubed plus x squared minus t equals 0. Okay, so how is this going to work? So n equals 1. So imagine we want to find a solution of this thing. So x is going to be some Puiseux series in T. So maybe I'll write it as c gamma t to the gamma and then plus higher terms. Gamma here is some rational number. So, okay, so we want this to be a solution, so we'll plug this into this equation here. So what do I get? So I'll get C gamma cubed, t to the 3 gamma plus higher terms, and then plus C gamma squared, t to the 2 gamma plus higher terms, minus. Okay. And I want this to equal 0, of course, right? So right here I have these lowest degree terms. 3 gamma is the exponent here, 2 gamma here, and the exponent is just 1 here. And you know, C gamma, of course, is non-zero, because I just take the first non-zero term. And so what needs to happen is that the lowest degree term here has to cancel out somehow, right? You know, 2 of these exponents, I have 3 gamma, 2 gamma, and the exponent 1. In order for some cancellation to happen, 2 of these exponents have to be equal to one another, and then one of them has to be larger, right? And then the coefficients have to cancel out. I guess all 3 could be the same, but it's too late. Yeah, okay. Maybe I'll leave this right here. How about that? Okay. Okay, so the lowest degree terms must cancel. Okay, so how can the lowest degree terms cancel? So there's 2 possibilities. So you know, maybe 3 gamma is equal to 2 gamma, and then those are both less than 1. So that will happen when gamma is 0. So either 3 gamma equals 2 gamma, which is less than or equal to 1. This is when gamma is 0. Or another thing that can happen is you could have that 1 is equal to 2 gamma, which is less than or equal to 3 gamma, and this is equivalent to just gamma equaling 1/2. Okay, so how did I get these? Actually, the third possibility, which is that 1 is equal to 3 gamma, which is less than 2 gamma, can't actually happen. So why is this? Well, we can actually figure out what gammas there are here by drawing a little picture. So here I'm going to plot, here I have 0, 2, and 3. These are the exponents in x that appear. So these are this is like the set A. And then I'm going to lift each of the points in A to a height given by basically the power of t that I'm assigning. So here, the constant term has just a single power of t. So I'll lift this guy up to the point 0, 1. And then the x squared and x cubed don't have any t, so that's like t to the 0. So I'll lift these guys up to height 0. And I'll just draw it higher than what I drew here just to distinguish them. Okay. So I get these 3 points here, and we draw them like this. And I actually get a triangle. Okay, and then, so what am I trying to do? So I'm trying to figure out what gamma should be so that, you know, I have the 2 lowest degree terms here canceling. So when I'm choosing gamma, and I'm sort of evaluating what exponent I get on a given term, then this is just evaluating the value of a linear functional on a given point. So for instance, if I am choosing a given value of gamma, then the exponent of t that I get here is just 3 times gamma. And so that will just correspond to evaluating the functional, which multiplies the first coordinate here by gamma, and then multiplies the second coordinate, well, I guess 0 in this case, but in general by 1, because that will correspond to the power of t on this coordinate here. So if I am evaluating the linear functional gamma 1 on each of these 3 points, that will tell me what the exponent of t in the lowest degree term is. And so what I want to find is I want to find what value of gamma is it such that the functional gamma 1 attains its minimum at 2 of these 3 points. And so that will just correspond to the lower faces of this picture. So if I take, this line, so this is, the direction 0, 1. If I take this line, this is the direction 0, 1. Then, this linear functional is minimized on these 2 points, and then this value is larger. And so that corresponds to this choice of gamma equals 0 that I took here. And likewise, I have this other lower face, this one. This is the direction 1/2, 1. Here. And this corresponds to gamma equals 1/2, and you'll see that it's minimized at these 2 points, and then this value is greater. So that corresponds to the second choice of gamma that I have here.
Ricky?
Yeah.
I don't know if you want to get into this or whether it's even correct what I'm guessing, but are we seeing in the background some tropical geometry?
Yes. Yes.
Okay, good. Because it seems like you are linearizing the polynomials and you are taking minimum.
Yeah. So in general, like a lot of the sort of work in one way of sort of formalizing how tropical geometry works is sort of in terms of Poiseuille valuations of these Poiseuille series for exactly this reason. Okay. So
maybe since you said yes, I'll ask another question. So is there can we view it not only as a reduction to the binomial system, but reduction of, so can one formally prove Bezout's theorem and Bernstein theorem from analogs that might be simpler in the tropical case?
I think that's sort of what you're doing, isn't it?
So okay.
I think that will more or less be kind of what this argument shows.
Okay.
Okay. All right. So once we have the value of gamma, so then it's very easy to figure out what coefficient we need here on C gamma. Right? When gamma equals 0, that's supposed to be when these 2 terms should cancel out, and so we just need these C gamma cubed and C gamma squared to cancel out. So C gamma is going to have to be -1. So from this, we know C gamma cubed plus C gamma squared is equal to 0, and this implies that C gamma is -1. And then likewise, for this one, we need which term? This -t is supposed to cancel out with this term, so we need C gamma squared to equal 1. This implies C gamma squared minus 1 is equal to 0. So this implies that C gamma is plus or minus 1. Okay, so that tells us what the lowest degree term of x of t has to be. It has to be either -1 or plus or minus t to the 1/2. Okay. And the claim is once we know the lowest degree term, right, so this right here. So we have solutions that look like x of t is -1 plus higher terms, or I say gamma to the 1/2 plus higher terms, or negative gamma to the 1/2 plus higher t to the, sorry. T to the 1/2. Okay. And then the question is, what are the higher terms going to be? And the claim is that you can basically just solve for what the higher terms are going to be, essentially using a version of Newton's method. So higher degree terms can be solved for using essentially Newton's method.
Somehow all these genericity assumptions you throw in that mean that these are simple roots.
Yes. Yeah, all of these, the generic thing also encompasses, like here we're going to need something about the Jacobian being non-zero, or the derivative being non-zero, but in general Jacobian being non-zero, and that is all going to be encompassed in choosing generic everything. I'm just going to talk a little bit, I'll just do part of this example so that it's kind of clear how it works. Of course, for the proof, you just need to check that you can basically just compute what the next lowest term is going to be, and then continue for as many terms as you want to compute. But in practice, what's going to happen is maybe we'll start with this solution, which we know starts with t to the 1/2, for instance. And then, if we compute f of x0, then what do we get? So the lowest degree term is, so it's t to the 3/2. In fact, there are no other terms, right? Because the x squared cancels out with the minus t. But of course, we want this to equal 0, so we have to do some sort of correction. So, we can compute like the derivative evaluated at x0, and we'll get something that looks like 2 t to the 1/2 plus higher degree terms. And so we can correct just by taking this to be, x0 minus the leading terms here, t to the 3/2 over 2 t to the 1/2, which is t to the 1/2 minus 1/2 t. And now if we were to compute f of x0, we would find that it would agree in like its first two terms. And then we could compute, what it's off by. F of x1 is, in this case, it's like minus 5/4 t squared plus higher order terms. The derivative is still going to be the same up to its lowest term. And then we'll do the same thing. We'll take x2 to be x1 minus the appropriate difference here. So we'll get t to the 1/2 minus 1/2 t, and then we'll just correct appropriately and get 5/8 t to the 3/2, and so forth. And so one can just check that basically whenever you do this, you just keep getting more of the terms agreeing, and so you just by doing an appropriate induction, you can show that you can compute arbitrarily many terms of this Puiseux series as you like. So I won't go into the details of this, but it's not too difficult. Okay. And again, in general, this is a one-dimensional case, so I'm just using the derivative here. But in general, you'll need to do the multi-dimensional analog. So instead of like dividing by the derivative, you'll need to do some multiplication by like the inverse of the Jacobian matrix. But it still works in essentially the same way. Okay.
I think the point is that you took, rather than solve a cubic, you solved two binomials.
Yeah, so in order to figure out what this leading coefficient was, right, I kind of just looked at the lowest terms which correspond to the single face, and those only had 2 points on them, and so I just had to solve a binomial equation in order to figure out what the coefficient was. And of course, that's going to be much easier than solving a cubic equation.
But in a higher dimension, it will be just a parallel pipette.
Yeah, and so what will happen in higher dimensions is it will be a parallel pipette, and we know how to solve those because that was one of the examples that I did earlier. Okay. So again, let me remind you of the situation since I erased it. So we have this fi hat, which is the sum of what is the sum of cia xa and then t to some power for each a in the set. Okay, and I want to find some solution of this, at least the lowest degree terms. And so we're going to write some solution, xit. Maybe it has lowest degree term yi times t to some power gamma I, and then these higher terms. So I'm just going to plug these guys into this f. So what do I get? I get just y to the a, coefficient times y to the a, and then times t to the gamma dot a plus wi. Okay. Right. When I take x, x has this xi has this t to the gamma I in it. When I plug that into this x to the a, I just get the inner product of the vector gamma with the vector a. It's my power of t, and then I get this extra wi of a. And so the point is that if I want to find the lowest degree term of this, what am I doing is I'm trying to just minimize this exponent. And this exponent is just, it's the evaluation of the linear functional gamma 1 on the point, right, this is just, so I'm evaluating like gamma comma 1 on the point a comma wi a. And so if I want to minimize this, just as in this picture here, right, what should I do? Well, I should lift each of my a up to height wia, and then I should try to find, this is some linear functional which is pointing upwards, so I should try to find some lower face of this kind of lifted picture, and then the direction, the normal direction of this is going to tell me what these exponents gamma have to be. So, to the lowest degree term is determined are determined by a lower face of this kind of lifted polytope. Remember, I took pi and then I lifted it. I have p down here, pi, and then I sort of lift it up to these heights. This gives me this pi hat. So the lowest degree terms are determined by a lower face of this lifted polytope pi hat, namely the lower face that minimizes this functional gamma 1. Okay, so now I have to figure out which of the lower faces I can actually find a solution. So which of these because remember, I not only need to, once I find the lower faces, I need that the coefficients cancel out appropriately, right? So in general, this lower face, let's ci be the lower face of pi that minimizes gamma 1. So we need to solve. But we're trying to solve for these coefficients yi. So we need to solve these equations, which look like so for each of these faces ci, we need to solve this equation in order to ensure that the coefficient that we get in front of this lowest degree term is actually 0. And what do we know? Well, we know, of course, the yi are supposed to be non-zero, because this is the leading term. The coefficient has to be non-zero. And so first, there has to be at least 2 terms in this guy, because if you just had a monomial, then there's, this is some generic coefficient. So if you have a monomial, there's going to be no way you can make this equal to 0 without setting a y equal to 0. So this ci has to have dimension at least 1. And remember that it has to be dimension at least 1 in all of the pi, right? And so one of the conditions of being a mixed subdivision is that the sum of these dimensions has to equal n for every lower face of the Minkowski sum of these p's. And so the only way that's possible is if all of the dimensions are just 1. And in that case, that means that these are just basically, each of the ci's is just a segment, and so this will just end up being a binomial. So we need dimension ci to be at least 1 to have a non-zero solution for y. And then by the mixed subdivision property, I'm actually going to sneak in an extra condition here, which is called being a fine mixed subdivision. We know that the dimension of the sum of the dimensions of the ci should equal n, and this implies that actually the dimension of each ci must equal to 1. So this we call a star. And what do these faces look like? These faces are ones which are just, Minkowski sums of one-dimensional pieces from each polytope. So these are exactly just the mixed cells in our mixed subdivision. So this corresponds. And so now we're basically done. Because what have we done? We've said that basically we can figure out what the leading terms are whenever we know that the gammas define a lower face of this lifted polytope, the Minkowski sum of these pi's, that is a mixed cell. And how do we figure out what the coefficients are in this case? Well, we just have to solve this binomial system. And we saw earlier that the number of solutions to the binomial system is just going to be the volume of this mixed cell. So, once we fix the exponents on the leading terms, then the number of solutions is going to be the volume of the corresponding mixed cell, if that functional determines a mixed cell. Otherwise, there are not going to be any solutions. And so the total number of solutions is just going to be the total volume of all of the mixed cells. This implies that the number of solutions for fixed gamma is just the volume of the corresponding mixed cell that minimizes gamma. Assuming that the face that minimizes gamma is in fact a mixed cell. And so the total number of solutions is just the total volume of the mixed cells, which is just the mixed volume of these polytopes. And then, so here we found the lowest degree terms, and then as before, we can just sort of easily solve for the higher degree terms using Newton's method. So this tells us that near zero, the number of solutions is just going to be equal to the mixed volume of these polytopes. And then using general facts from algebraic geometry or some sort of implicit function theorem thing, or some general result of that form, we get that the number of solutions at t equals 1 is certainly bounded by this number, and for general choices of coordinates, for general choices of coefficients, y should be equal to this number. So, so that is essentially the proof, and I think I'm all out of time, so I will just leave it there.
Yeah, wow, yeah. Yeah, this was great. So any questions to Ricky? So just a simple question. This, what you use of algebraic geometry to know what you need is basically Nullstellensatz or something more complex?
I'm just trying to think. So let's see. So the degree, right? It's basically that like degree is well defined as, in algebraic geometry, it's defined as some sort of degree of a field extension. And so the fact is that like at a general, I forget exactly what it comes down to.
Okay, no, it's not so important. I was just wondering if it's some, what kind of fact from algebraic geometry it is. But yeah, if it's not easy to explain, then maybe I'll ask you separately.
Yeah, a degree of a map. Yeah, I mean, again, it just sort of comes down to some fact about if you have some degree of some algebraic map. So this is usually defined as sort of the degree of a certain field extension, and that determines the number of pre-images of a given point. And the point is that like you can get fewer than that, but in order for that to happen, it needs to satisfy there has to be some sort of discriminant or something that equals 0. And so like that, it doesn't happen for generic points. But I don't remember exactly what the key theorem is.
I mean, it might be like come from the fundamental theorem of algebra, right?
It might just be some sort of fundamental theorem of algebra.
Well, I was just hoping you would not say it's Bezout's theorem, because
no, I don't think. I think it's relatively simple.
Because Bezout is in some sense a generalization, right, of the the fundamental theorem of algebra, in which you
right.
Yeah. Okay, more questions to Ricky.
I guess one comment that I also have is that a lot of times here I was just saying like for generic choices, blah. So you can actually like write down sufficient sort of how generic it has to be in terms of not satisfying certain equations, because I mean basically it comes down to being able to solve for certain coefficients. Like for given choices of these C's, you need to be able to solve various binomial systems. So you can actually like write down what the genericity conditions you need are, so that you can potentially in practice check that they're satisfied. And also, maybe you're not interested in computing things over complex numbers, but you're interested in things over like other fields, perhaps a positive characteristic. So there is a version of Bernstein's theorem that also holds for general algebraically closed fields due to Rojas. The statement is more or less the same as the one that I gave, but you just replace C with an appropriate algebraically closed field.
Okay.
And so that should still give you bounds even if you're not over an algebraically closed field.
Yeah, so if you're not algebraically closed, you get some large upper bound, potentially, because as we know, for instance, for reals, often you're going to get many fewer solutions than over complex, but it's something at least.
Right, more questions. So I, for one, would love to see applications, but yeah, I'll write you separately
Okay.
about this. So let's thank Ricky again. Thank you.